In this second part, we're going to look at C++ structures and classes, which actually turn out to be very similar. So what we're going to look at is using classes to encapsulate data as we did with structures, but we're also going to add APIs, or member functions as they're known, which operate on that data. So you can think of an object in software a bit like a component in hardware. Inside you've got state, which is the output levels of D-type flip-flops, JK flip-flops, registers, etc. And you've got operations you can perform on internal state. We typically access these through interfaces like SPI, I2C, or parallel interfaces. And when you use a component in a circuit board, you don't care necessarily what's inside. You might see a sort of system diagram in a data sheet, but you don't really need to know. You just need to know how to communicate with it and how to pass data to it and how to get the desired result back. And this is the same aspiration, only in software. So this is important. Component-based software development enables us to build reusable code that hides away the unnecessary details, exposes only the things you need access to, and hopefully also mops up a lot of the common tasks so you don't have to remember to do them. So that's kind of saying where we're going with this. So let's look at first of all structures and functions and how we would use C to build an API along the lines I've just said, and then look at how a C++ structural class can automate some of the boilerplate code that we would otherwise have to write ourselves. Okay, so let's start with the familiar example of a human, struct human. And what we might say is, okay, I want to be able to do a couple of things here. I want to be able to display the information about a particular human, and I want to calculate that person's body mass index. So in this example here, I've written the structure, and these are the prototypes for the two functions I'm going to actually write in a minute. So this is what would appear in a header file, which is a description of the structure, that's the data type, and the prototype of the methods or APIs, as they're sometimes called, that operate on this data. So notice they take a structure as a parameter. This one takes one by value, this one takes one by reference. So let's look at the concrete implementation of those. And I've used a by reference and structure on purpose. Now, notice that we need always access to the particular instance of a structure that we're talking about. So in the case of the display one, okay, you may have many instances of human. Okay, you can have struct human Fred, struct human Rod, struct human Shirley, whatever it is. Okay, and we need to know which of those variables we're operating on when we call this function. So naturally we pass in either a copy of the data, as in the case of the display one, and that prints it out. Prints out the weight, body mass index, and a little star if the BMI is over 25, not to be taken as a diagnostic criteria, by the way. And this one, the calculate BMI, I've used the other approach I mentioned, which is to pass in a reference, or a pointer as it's known, to a type human. Now notice the star can either be on the end of the N or before the parameter name. Both mean the same thing. I prefer human star space H, but most people do it the other way around. Now note also, we're using this arrow notation. So again, we need a reference to the variable itself, so then we can calculate its BMI from its weight and its height. Okay, but we've got to pass that every time. Otherwise, which piece of information are we talking about? So the first parameter, and in this case the only parameter, is a pointer. A pointer to a variable in memory that already exists. So let's look at how we would do this in code. It's very straightforward. We'd first instantiate this person. So struct human's the data type, and then we'd initialize it with some values, and then we would pass the address of it calculate human BMI. So that will take these parameters and overwrite the BMI property. Okay, so we're passing the address. Now, it's really important because we could have many of these. Struct human person 1, person 2, person 3, a whole array of them, all sorts of things. This function needs to know which one are we modifying, what's reading and modifying. Okay, and then we perform this calculation in place. So this is modifying person 2. Now, so what, you might say? Okay, now there are some common errors that are made. That is use before initialization. So if I didn't set the age, weight and height and then started to calculate the BMI, what data is it using? Is it zeros? Is it something else? All right. Reading the BMI before you've actually performed the calculation. So let's say you'd initialized the structure, but you hadn't called calculate BMI, and then you read the BMI property. It's not been set, so it's some random value or 0. And then, more sinister, update without recalculation. So you might change the weight, for example, and then forget to recalculate the body mass index. So these are things you've got to always remember yourself when you're using structures and an API. Right. Now, there is a demo video which looks at some of these things. If we have a quick look through, again, I ask you to go back to the slides and watch this through fully, all right, because it talks you through quite a few things, and it goes through some of those scenarios. So the first one, we've got human person 1, we initialize it with each property individually, calculate the BMI and display it, and we get a sensible value, 24.4. The next one initializes it using the curly brackets. Hang on, just pause that. And then we update the BMI, or calculate the BMI. That's all fine, that displays correctly as well. Then, this third example, we don't actually initialize it. Turns out that the member variables are initialized to 0. So when you divide by 0, you get inf. So for floats and doubles, if you divide by 0, you've got infinity as a valid result. Now this has happened at runtime. Yeah, this code is now running. It's in the customer's hand. It's already, there's no compiler error, nothing. A sophisticated static analyzer might spot the mistake, but the compiler won't. All right, and the only thing that's going to find this mistake is you scrutinizing your code and thinking, noticing what isn't there. All right, which is to calculate the BMI before you display. All right, you look at that, you'd think that would work if you were naive and new to this code. So these are the risks. So we've not calculated BMI, so we get 0 for body mass index. Right, and then the most sinister of all, here I'm going to take person 2, which already has been calculated properly. I'm now going to tweak the weight to a different value. And when I display the BMI, it's based on the old value because we haven't recalculated it. So what we're saying is that the BMI value is dirty, right? It's based on old data. It needs updating, and I've forgotten to update it. So those are some of the common errors that you get. So here they are in summary. So person 2's been initialized. We calculate BMI, display, fine. Now look at the mistakes. Forget to initialize. Brace yourself. Hopefully you're going to get nonsense coming out. Use before calculation. So you've initialized it, but you didn't calculate BMI, and then you try to display it and you get rubbish. And most of all, the worst of all, because everything looks normal with this one, we've already got person 2 set up. That's up here. That was all done properly. But weight was 97. It's now changed to 65. Crumbs, that's a big change. And this will be displaying the BMI based on 97. So things that can go wrong so easily, particularly when you're working with someone else's code or your code after about, say, 6 months when you haven't looked at it. All right, so let's look at the struct-based API. API stands for Application Programming Interface. APIs, really, each of these is one of those. So this is an interface to this. All right. So display human, pass a human in, displays it. Calculate BMI, pass in the address of an instance of human, it'll update the BMI field. Init human, passing the age, weight and height, and you get back a instance of human. So that's good. That means that if we always use the init thing, we'll never forget to initialize. Update age, pass in the age, pass in a pointer to the variable that we're using, and then this one will modify its BMI as well and its age. Okay, so that's the idea. If we always pass in a reference to the variable, type struct variable that we're working with, person 1, person 2, person 3, whichever one it is, then when we set the age, set the weight, set the height, it can not only set those properties in line, it will also update any calculations that need to be updated automatically. So as long as we use the APIs, it basically doesn't go wrong. All right, so we always initialize with the init function. That saves us forgetting to initialize. Whenever we do that, it will automatically calculate the BMI. So we can't forget to do the calculation. If we update the weight, it will automatically, inside this function, update the BMI as well. Same for the height. For the age, it won't bother because it doesn't change it. Okay, so the rule is use the APIs, don't modify the member variables inside the structure. Okay, so don't modify the members of a structure directly, use the APIs. And if we write them carefully enough, we can fix those common problems. So for example here, if we always create our structure using the init function, okay, this returns a structure which gets copied into person 3. We've got to pass in the parameters that we do know, therefore it'll always be initialized. The other thing this would do is call calculate human BMI for us every time we initialize, so we don't actually forget to calculate. Same, that's the point made here. So here, not only are we initializing it, but inside init human, there'll be a function call to call calculate human BMI. Because you're updating the state, it'll then update the calculated parameters automatically. And the same if you update. So if we call update weight, we pass in the object that we're changing, right, the address of the variable, we give the new weight. That will not only set the weight, but it will also recalculate the BMI so that when you display it. So what I'm saying, long way round, saying a simple thing, if you always use an API, you can write that API to engineer away these common mistakes and things you forget. All right. Now that's with C and structures. And it's not bulletproof, it's not foolproof. And the reason is that if you create an instance of a structure, a variable, here it's called person 2, and you press dot, you'll see this pop up in some editors, and they can still change the parameter and basically go around the API and not use it. And that is a limitation, unfortunately. Now, when you consider that the person writing this code maybe didn't write your structure or associated header files or whatever, then they may do this thinking it's perfectly okay and making a mistake. So the limitation with C is we can't enforce rules to stop this happening. Now that is different with C++. This is actually a video going through some of the things I've just said, so I'm going to skip this. Use the video in the slide, make sure you watch it. So sorry, it's a video in a video. Right, so let's look at classes. Now, a class is a bit like a structure. It has a similar sort of shape in the way it's declared. And within a class, we'll find essentially two things: data and functions. Now, without going into too much detail, a class has one copy of the functions. okay, in memory. So as soon as you use a class as a data type, all the functions in it will be somewhere in memory so that they can be called. Each instance of the class, or each variable with the type of the class, will have its own copy of its own data. So much like a structure. Let's look at this a bit more closely. So the anatomy of a class will be class, a class name, and then curly brackets. Right? You'll have some variables in there like you do with a structure. You'll have some functions, unlike C structures. Okay. Now, the way this works is that the member functions, as they're known, belong to the class. And they have access to all other functions and all variables in the class. That's different from the outside looking in, where you'll have limitations and you can enforce rules about that. You also have two very special functions known as a constructor and a destructor. Constructors get called when you create an instance of a class, in other words, when you create a variable of that type, and the destructor gets called when it goes out of scope or is deleted. Okay, so if we remember our BMI example, where we had a structure, we wrote this API, and you'll notice that we had to pass in a pointer to a type human, because these were just global functions, update weight, update height, of this human. Now I emphasize the word this, right? That parameter, right? So this is the new weight, this is the new height. So you want to update this human's height, this human's weight, so we could modify this in place, right? Now again, I'm emphasizing the word this one, right? Because we could have hundreds of them, we could have an array of them. Which one are we changing, right? So with C, with our API, we had to pass in which one it is. It's this one or it's this one, right? Okay. With C++, this, the instance you're modifying is given to you, and you don't have to pass it as a parameter. It's a hidden one. We'll come to that in a minute. Let's look at the BMI example. Now, a few things to explain here. We have lots of sections here. First of all, we have, like the structure, some instance variables. Okay, these are just built-in data types in this case, but I've used a convention, and it's only a convention, of putting an underscore on the front. This is just a reminder that this is an instance variable. So like a structure, it's inside it, but we've got this word private, right? And what that means is that only functions that belong to the class can access this directly. More on that in a minute. Next point of interest is the first function that we define in here, which is known as a constructor. And we can recognize a constructor by two things, really. The name, which is the same as the class, and the fact that it has nothing written for the return type. No void, no integer, nothing. It's just missing. All right? That's a constructor, and that's a special function that gets called every time you create something of type C human, automatically. And in fact, when you do that, you're forced to give it the age, weight, and height. Okay, as we'll see. Following on below, we see two groups of member functions. The top group is in a public area, so these can be called from outside the class in a special way. The private member functions, however, are invisible to anything outside the class. Update BMI, if we do this right, should never need to be called directly. Setting the height, weight with update weight and height will automatically call this if we do things properly. Constructing a new type C human will also call update BMI directly, as we'll see. All right. But if we do this well, the user should never have to call it. So therefore, update BMI is a private member function which is only visible and usable inside the class. What do we mean by inside the class? Right. So far here we've got no code. Right. We've just declared a class. We've described what it's like. So yeah, we've declared some variables, but we've declared some functions. We're saying, hey, There's a function called height that returns a float. And look, there's a function called update weight that takes a double and returns a float. All right. So where's the code? Well, you could have written it right here in the header, but that makes the header very long and it's showing the whole world your code. Sometimes you just give them the header file and a compiled library so that you can hide your implementation, because it might be commercially sensitive, or it might be that it's just you don't want people messing with it. So here is this is the header, chuman.h or .hpp. Now let's look at its mate, the CPP file. All right, there's the header just as a reminder. So we've included the header file, and a member function, that's this little lot, has a prefix of chuman : : so the class name : : okay, so normally it'd be return type, class name : : function name. Now the constructor has no return type. Now notice this. There's a hidden parameter in here, which is a point. If you've go back to the structures, remember we passed a pointer to the actual variable that we are changing so that we can change it here in this function. Well, that's implied. You get that automatically, and it's called this instance, right? It's a pointer, so we use the arrow notation. So this age equals age, so we copy this age into the member variable age, and this is very explicit. Look, it's the member variable, this age, this weight, underscore weight. So that's the other thing, we've got the underscores, equals weight, and this height equals height. So when we create an instance of this variable, as you'll see, you'll have to pass these parameters in, and they'll get copied in, and look, then we update the BMI. So in the process of initialization, we're not only making a copy of age, weight, and height and storing them away, we're also then calculating the BMI based on this new data automatically. Here is the update BMI function. This can only be called from one of these functions. They're members of the class. From outside, this won't be visible. This BMI equals this weight divided by the height squared. And so we go on. A few others of interest. Okay, so these, as I said, we're not allowing outside access to these variables, age, weight, height, and BMI with the underscore, but we write accessors. This is a read accessor. I've just used the name of the variable, weight, and we're returning a copy of the weight. Now this doesn't get us a reference to the original, this is just a copy. That's a read-only API. Returns a float and a float for height. And the same for the BMI. If we want to read what the BMI is, we can do variable name dot BMI, open bracket, close bracket, call the function, and that returns a copy of the BMI. Update weight, we pass in a double. Okay. I don't know why I didn't use a float there. I think it's because the BMI calculation wants to be accurate. I think that was my thinking. Anyway, so we pass in the new weight, make a copy of the old one. All right. Update with the new one, recalculate the BMI, and return the old. This is a standard trick you see a lot. If you're going to pass in a new value, it returns the previous value in case you want to use it like measuring a difference or something. It's a quick way of doing that. Or we could just disregard this thing. And same for height. So we pass in a new height, we make a copy of the old one temporarily, overwrite the height, recalculate the BMI. Oh yes, you can see, yeah, I don't know why these aren't floats. And then we return the old one. All right. So that's the concrete implementation of the class. So the class contains both data and functions, known as member functions. And the data is known as member variables, or its state. Right? So normally you go return type, class name, : function name, and then whatever parameters. All right. So remember, member functions have access to all the data inside the class, be it private or public. And the this pointer is, instead of passing the pointer to the instance that we're changing. We get that for free. Think of it as a hidden first parameter, which is probably how it's implemented. Right. So we're going to just stick to private and public for now. Protected is an object-orientated addition, which we haven't covered yet, so I'm not going to discuss that one quite yet. Private, only visible to within the class, internal use only. Public is for your APIs. Right, so all of these functions can access these. So you only access these through the functions. So how will we create one and use one? Well, the data type is the class name. So person2 equals chuman brackets 4597 1.9. Now there's no other way to create a chuman because I have written one constructor that insists on having 3 parameters, an int, float, float. Okay, so that solves the initialization problem and has also called update BMI to get an up-to-date value. I can then display it. If I call update weight, that will set the weight to the new value, recalculate the BMI, so when I display it, it's correct. But the good news is what you can't do is access these. So person2 dot underscore height. This is what we mean by outside access. So we've got the variable. You press a dot, and the only things that can follow are public things. Anything else, the compiler will reject it. So that will get a compile error. You won't even get to run the code. All right. Let's take a closer look at this. The constructor. The beauty of the constructor is it forces you to give the information it needs to initialize the class. And it can also, it has to be run. You can't create a type chuman without using the constructor. You can have many different constructors with different parameter types if you wish. So be careful, but you can. Right? It's guaranteed to run, and so you can put things like initialization in there. So when you use digital out in embed, you pass a pin number. You can also pass an initial value, but by default you can just pass a pin number. You've got no other way of creating digital out. You've got to give it a pin number, because that constructor sorts out the pin mappings, sets it to an output, sets the speed, sets it to push pull, yeah, and sets the initial value to be low by default. You can override that if you wish, but yes, that's what it does. So all that setup, oh, and switching on the clock. Christ, how can I forget? Yeah, there you go. I may have forgotten. So by just creating an instance of digital out, the constructor will set it up for you so that everything's ready to go. You can just switch it on and off. That's the idea, and you can't forget because it's a common operation that's done. All right. So yeah, constructor, when we invoke it, this is the code here. So person2, the address of that is this, right? So the first thing it'll do is it'll create enough memory to hold all these variables. Remember the code, there's only one copy of the code in memory. That's already somewhere else. It's in a read-only area of memory, hopefully, right? Because you're only going to run it, you're not going to modify it. The data makes up the instance of a class. All right, so person2, so what will happen is memory will be allocated either on the stack or if it's global on the heap. It will update age, weight and height with these values that you pass to it, and you've got to pass them. There's no, or it won't compile. And then the BMI will be updated as well. So that's how the constructor works. The general member functions, again, we can construct an object of type human by calling the constructor. We can update the weight, which will then also automatically update the BMI. If we look at update weight, this is what happens. Note it calls update BMI. We can overwrite the member value. Now, as someone pointed out when I gave this lecture, if you're going to be MISRA compliant, you would put this arrow, but if you don't, it'll still compile. Right, it assumes it's this. All right, that's asking for, if you get typos and it happens to match a global variable, then you may make a mistake. So they say always put this, right, when reading and writing. I haven't here, but at least it illustrates the difference. All right, and basically when we update the weight, we're also updating the BMI. The user doesn't need to care about that. They just need to know it works. That calls a private member function, right? So here we couldn't go .update BMI because it won't be visible. You can't call it. It's private. But from within inside the update weight, which is public, it will call it on a needs basis. So what we've achieved is encapsulation, which is what a chip does. So we think of a chip, we don't usually think too hard about what's inside. We might have a look at it from a system level, but we're certainly not going to look at it at gate level, or certainly not transistor level, but someone has to, or something has to. We've encapsulated state, which is your member variables, and methods to operate on that state, which is your APIs. And so, in a way, what we've built is a software component. So you've got your private variables and private methods, which are internal use only. Yeah, can't see those from the outside, can't access them. Bit like a chip. You can't use these pins to access everything in the chip, right? You don't want people to. It could be dangerous. And then you've got the public APIs for modifying this. Now, it is possible to have public members as well, variables. Generally frowned on. It'll let you do it if you put them in a public scope. Don't do it. Now, there's a video demo here of that very example. I suggest you watch that one. We see it working in action. If you want to know a bit more about data encapsulation in classes, there's a nice link you can have a look at. There's also a video on Panopto that uses classes for complex numbers, which is very nice, and you'll see some of the more interesting features. Go and check out that video. It's on the Panopto repository on your module site. And next up, we're going to take it on a stage. So far we've just used classes to encapsulate data, okay, and to provide an API interface so that things don't get forgotten. What we haven't yet talked about is reuse, how we can write multiple classes, a hierarchy of them, in order to share code between different classes, exhibit different runtime behaviors, and lots of interesting things like this. All right, we're not going to go into great depth about that, but it's going to be covered. And then we'll go back to embed and start having a proper look at how we interface to the analog world in a way that is safe and it maintains data integrity. And you might be surprised how things you thought you knew how to do, you actually didn't. That's especially important for the robotics students because they don't do digital signal processing. The electronic engineering students do. So there's some basic DSP, digital signal processing or sampling theory, in that lecture, and that's very important. Okay, I'll leave it there.